Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the Turbulence at the Exascale podcast. For those not familiar with the podcast, what we are trying to do here is we are trying to gather the view of the community regarding exascale computing for turbulence research in the UK, and we are trying to identify what are the challenges and opportunities about exascale computing for turbulence research. So this podcast is linked with the ExCALIBUR initiative, which is a big program that was launched in the UK last year. It's led by the Met Office, the UK Atomic Energy Authority, and the UK Research Innovation. And it aims to deliver research and innovative algorithm developments to harness the power of exascale computing in the UK. And so I'm leading the working group on turbulent flows, and this podcast is also a part of the UK Turbulence Consortium. So today my guest is Michèle Weiland. Good afternoon, Michèle.
Good afternoon.
So Michèle is working at the Edinburgh Parallel Computing Centre. You obviously know EPCC. This is where Archer and Archer 2 are based, and Michèle is a senior research fellow, and she's also project managers on a lot of UK and European projects. As you can imagine, she's an expert in high performance computing, software performance analysis, and novel programming model. Right, so without more talking on my side, I'm going to ask you, Michèle, to tell us more about yourself, where you're from, what you have studied, and how did you end up working at EPCC?
Well, first of all, thank you very much for the invite to talk at this podcast. It's a pleasure. So yes, thank you for the introduction as well. I am originally from Luxembourg, in fact, so that's where I grew up. And then went on to study in Germany, in Heidelberg. I studied medical informatics, did that for 3 years, and then decided to do a year abroad in Edinburgh. So I came to Edinburgh to do my 1 year studying computing at Edinburgh Napier University, in fact. But at the end of that year, I was due to go back to Germany and finish my degree in medical informatics, but in fact, I was offered a PhD position instead at Edinburgh University. So I decided I wouldn't bother going back to Germany and finish that degree. I started doing a PhD instead. And that was in machine learning applied to music. So looking at learning musical structures and using that information to generate new music. So that was a fairly long time ago now. And at the end of that PhD, towards the end, positions came available at EPCC, so applied to join EPCC, and that's how I got to EPCC. I started 15 years ago, and I'm still here.
Very good. And may I ask you, how did you become interested in I will say computer science, but like machine learning and high performance computing?
So my interest was in computer science all along. So when I did my medical informatics degree, it was really the computing side that I was interested in, applied to medicine. And before that, I've always been interested in music. So when this PhD position came up and I was offered it, that was just an ideal mix. I became interested in HPC. I didn't really know anything about HPC, to be honest, for a long time. But when I was doing at the end of my PhD, I was training large models, and I was doing it on, my laptop, and it was slow. I mean, very slow. And I remember talking to somebody, because I was at Edinburgh University doing my PhD. I remember somebody saying, "Have you heard of EPCC? They do like high performance computing, and you can make things fast by making them parallel." And I thought, wow, that sounds amazing. And as I said, then jobs came up. That was right towards the end of my PhD. Jobs came up. I hadn't quite finished my PhD, but I applied for the job, and I was in my write-up phase. So I started working at EPCC while also finishing my PhD. But EPCC offered, when you start, really, you don't need to know anything about HPC as such. You just attend the training courses. In this case, I joined some of the MSc classes, learned about parallel programming. And because I had a computer science background, that was really all I needed. And then I learned from there.
Fantastic. So I know you have been working from home from quite some time, but I wanted to ask you, what's the best thing about working at EPCC? What do you really enjoy about your current position?
Yeah, so EPCC appealed to me. The reason I applied for it years and years and years ago is because I looked at the website, not knowing anything about it. I looked at the website and I just saw the vast number of things that happen, the huge range of projects. And I started off as an applications consultant, which is probably what nowadays you'd call an RSC.
Mm-hmm.
But you get just put on any project. So I've done projects in evolutionary biology, in astrophysics, in weather, in engineering, everything. And you sort of get thrown in at the deep end, and the variety is just immense. So that's something that really appeals to me, the broad mix of application domains, the scientists you work with, the variety of machines you get to work with. I mean, you get to play with everything. And to be honest, the mix of people as well. So when I started EPCC 15 years ago, there was about 60 of us. We're now about 110. So we've grown a lot, but the background from people is very, very broad. So people can have backgrounds that are not even related to computing. They maybe have done a humanities degree and converted into computing. And I really enjoy that. I like the fact that people have a very, very broad outlook on the work they're doing. So that appeals to me.
Great, thank you. You said you have been involved and you are involved in a broad range of projects. So my next question, I'm curious, on what projects are you currently working on at the moment?
So two main ones. One is an ExCALIBUR project called Element. This is all about meshing, all the problems that meshing has for the exascale, at the exascale, how to make it scale, how to make the IO work better, all those sort of things. So that's only a small project, I guess, in the greater scheme of things, but some of my time is spent on that. Most of my time is spent on the Asimov Strategic Prosperity Partnership with Rolls-Royce. This is a 5-year project. We're now 2 years in, just over 2 years, I guess, into it. And this is all about building the world's first virtual full gas turbine, effectively. So that's a large collaboration. So it's Rolls-Royce and Edinburgh lead this project, but it also has Cambridge, Oxford, Bristol, and Warwick as partners. So it's quite a big undertaking.
Fantastic. Great. Right. So this podcast is about exascale computing. So we are going to talk a little bit about that. And I know you have been involved in a European project called Exaflow. So can you tell us more about what were the objectives of this project and what did you manage to achieve with respect to the transition to exascale computing?
Right. So this was one of the European exascale projects starting in 2015, if I'm not mistaken. So this was all about, Exaflow is all about moving CFD codes to the exascale, looking at both the algorithms and the implementations of those algorithms on a large scale. So from EPCC's point of view, we weren't so much involved in the algorithm side. That was left to the scientists, if you want. But we very much looked at, once you have decided on the algorithms, how do you implement these to be efficient? And by efficient, I mean both performance efficient and power efficient as well, and IO efficient. So we did a lot of work on scaling the applications, doing performance analysis, doing power measurements as well, and seeing what we could do to improve them. So at the end of this project, it was a 3-year project. We managed to do a fair number of large-scale runs with improved performance, so in particular improving the IO. There's one big piece of work we did. We also did quite a lot of studies around improving the power efficiency. So that was looking at things like MPI only versus MPI and OpenMP. See if that reduces the power without really limiting the performance. those sort of things. So this was an interesting project because it looked at both academic codes and industry codes as well. So the academic codes like Nectar++, and then there were industry codes used by a center from Stuttgart, the Advanced Computing Center for Automotive Simulations. They're attached to HLRS. And so looking at very, very different scales here, the academic codes scaled really well, the commercial codes, not so much. So that was an interesting experience as well.
Great. And I have a similar question for another European project about IOs called Nextgen IOs. So once again, can you tell us more about that one? And maybe if you can tell us more about how do you think we should manage IO for at an exascale level?
Yeah, so Nextgen IO is sort of similar range of project as Exaflow. It was a long time ago now, it's probably about 2013, 14. Intel approached us to say, we're developing this amazing new memory technology. We should do a project together. So we put together a consortium together with Intel that included Fujitsu and a few end users. And the idea of the project was to develop a system, the actual hardware and the software on top of it that would use this new memory technology. And the new memory technology is now called, it didn't have a name at the time, but it's now called data center persistent memory. And it is non-volatile memory, which means that you can turn the power off and the data is still there. There's non-volatile memory, but it is byte addressable. So unlike an SSD that isn't byte addressable, this is just like memory, just like DRAM, but it is non-volatile. And so this project was really all about, Intel developing this technology. There isn't really an understanding of how this would be useful in HPC. So the project was all about looking at various use cases, and trying to understand how the technology can be made useful for HPC to accelerate IO, looking towards the exascale. And so what we did, as I said, we had a range of use cases. One was weather related, one was CFD related, looking at OpenFOAM in particular. And so we built the hardware platform with Intel and Fujitsu. So we've got a prototype system that is sitting at EPCC. And then we looked at what we needed to do to improve IO performance. So this memory is really fast if you compare it to an SSD, but it's quite slow if you compare it to DRAM. So it's another step in a hierarchy. And you can use it as memory, or you can use it as storage. And if you use it as storage, you can just write files to it if you want. So, but these files are node local. So if you want to have a distributed file system, things can become a bit more complicated. You need an extra layer of software on top of that. So what we did for something like OpenFOAM, for instance, OpenFOAM has terrible IO. Although I do, I'm quite fond of OpenFOAM for some reasons, but the IO is not great. And something you can do very easily is just write files to this very fast storage on the nodes. So that's a very simple solution. But obviously, going towards exascale, that may not be possible because your application may not do that sort of IO. So OpenFOAM, for instance, is nice because you write once and you don't read the data back ever. Looking towards the exascale, what we will need to do is probably use the entire stack of the hierarchy from memory down towards storage and make sure we intelligently place the data where it needs to be. Only put it into fast storage if we want to, use it again, and make sure that the user or the scientist is sort of separated away from the process of where the data needs to go. Engineers don't care whether their data sits on a spinning disk or on an SSD or even on a memory map file system. So we need to sort of extract these things away intelligently without creating too many overheads in doing so. So quite a long answer to very simple. You could put it very simply and just say it's complicated. But
yes.
but the Nextgen IO system is interesting because it allows us to experiment with these sort of hierarchies of I/O and storage speeds.
The system that you built with Intel and Fujitsu is still on and available.
Yeah, it is available. So it's not huge. It's 34 nodes, so 34 nodes at 48 cores each. You can do the math. It's been running for a year. It's going to be running for another 2 at least. So after the project, we had a requirement to run the system for 3 years, make it available for free to researchers. So people that want to use it just need to get in touch and they can get an account. And it's got, per node, it's got 3 terabytes of non-volatile memory. So all in all, it's got 100 terabytes of non-volatile memory on the entire system.
And sorry, I'm becoming curious. The system is still relevant for the future supercomputers that are going to be built by Intel and Fujitsu, or the technology
yes.
is maybe not.
The technology, so the DCPM technology itself is only in the first generation. There'll be other generations of it. It was only released in April 2019 as a product, so that's new. And the compute nodes on that system are Cascade Lake Intel. So, and it's got you know, a dual rail interconnect. So from all those points of view, it is you know, it's not the latest cutting edge hardware, but from the design principles. So it's got fairly fat nodes. It's got a lot of non-volatile memory per node, and it's got the byte addressability is what is important. So yes, if you want to explore large memory and persistent memory and fast storage in a hierarchy, it's a very relevant system. It's just not, it's not for exascale, you know, it's not huge. It's got 70 or so cores. It is what it is. But in order to test the storage hierarchy, yes, it's very relevant.
Great, thank you very much. Right, I have another question on another aspect of your job. I know you've been working on with the Met Office NERC cloud model. So can you tell us more about this cloud model?
Yeah, so this is also going a fair few years back now. We talked to the Met Office, Miss 2013-14 again, and they had a model to model clouds called the LEM, which stands for Large Eddy Model. But they had an issue with it, as in it didn't scale. They couldn't run large enough domains with it. And the reason for that was that the decomposition of the model was hard-coded into the model. So it could only do a 1D decomposition in a 3D domain. And the way it was split up is to basically limit to 512 core runs. And that just was, you know, not big enough any longer. So we talked to them and got some funding in to fix this. And initially, in fact, we were just going to fix the LEM. But the more we looked at it, the more we realized that actually it'd be quicker to just start again. So we then basically redesigned the LEM entirely, called it MONK. MONK stands for Met Office NERC Cloud Model. And we designed it to be, so we took all the physics in the LEM were fine. So we took all the physics and effectively ported it over to MONK, just made it good, went from Fortran 77 to Fortran 2008. And then we used a very modular, very pluggable design, software design. So the idea was that any Met Office scientist should be able to write their own plugins for the code, but that the core of the code was well tested and sort of in place. So we would provide things like domain decomposition modules, parallelization modules, utilities, all well tested and in the core. But the scientist can write their own plugins, and they just basically change the configuration file and pull these plugins in. So if they wanted to change the decomposition, they can do so, but the main decomposition will be provided by us. And so we did that, allowing us to do different decompositions, different solvers, FFT versus iterative, and so on. And yeah, we changed the code, and we have on Archer, I think the largest number of cores we've run it on was 32,000, just because we didn't have the budget to run more, but it would scale higher than that. So we went from a code that scaled on 500, maximum was 512 cores, to one that we ran up to 30,000, no bother. And it's been, it's proved really successful, because you can now run as large a domain as you want. You're no longer constrained by this decomposition.
Great, amazing. Right, now I have a question about exascale computing, and from your perspective as a HPC expert and involved in a lot of projects, what do you think are the main challenges associated with exascale computing? I mean, we talked about IOs, but is there anything that you say, well, we are going to struggle with this and this and this?
Yeah, I mean, the main challenge going to exascale is just the level of parallelism. And the first challenge is finding it in your application. So exposing the level of parallelism, you need to have parallelism in order to use an exascale computer. But even once you've found that parallelism, really the challenge is how you use it and how you map it to the hardware that you have. Because with lots and lots of parallelism become lots and lots of challenges. Things like variability in the performance of the nodes, lots and lots of data flying around on the network, lots and lots of data having to be written to disk. Load balancing is going to be a huge issue. Even if you have a code that is trivially parallel, there'll still be performance variations. As soon as you have to synchronize in the code, there could be, you could spend a huge amount of time doing nothing. And while that is costly on 1,000 cores, on 1,000,000 cores, that is really going to be devastating to performance. So in my mind, exposing the parallelism is the first challenge. But once you have found the parallelism, managing that parallelism in such a way that you don't cripple performance on your system, just synchronizing or flooding the network, that is going to be the next big challenge.
Good. And well, you said at the start you're involved in an ExCALIBUR project about meshing. So how are we going to do meshing on an exascale computer? It's a very silly question, but.
No, it's not. Well, the first question is, do we have to do meshing on an exascale computer? Or do we have to just do meshing for an exascale computer? So those are the sort of questions we're talking about. If you want to create a mesh that is of sufficient quality for exascale computation, ideally you want to generate that on the exascale computer, because it's in place and it's going to be huge. But the mesh generation may not have to happen at the exascale. So you may also want to just do it, on a system that is next to your exascale computer, very large shared memory system, for instance. So those are the sort of challenges that isn't actually, it's not a silly question at all, because it's actually, the answer is not clear. It's actually very unclear whether you actually need to do it on an exascale computer or just for your exascale simulation. Great.
So you have been working for EPCC for quite some time now, so you have a good understanding of the UK landscape, I will say, in terms of supercomputers. Do you think the community who is using high performance computing is ready for the transition to exascale computing? And do you think some communities are more ready than others?
Yeah, the latter. Some communities are more ready than others. And I think, I don't think anybody's truly ready, because you don't know if you're ready until you are faced with the reality on some level. You can believe you're ready, but you might not be. Some communities are very well organized, I think, and the communities and the codes I think that will do best are the ones that are used in the broadest setting. What I mean by that is that if people have only ever used, say, Archer, right, and then they move to Archer 2, they already get a shock, because it's different, very different architecture. But if you have people or codes or communities that are used to using a range of systems and sort of understand what different networks, CPUs, memory, bandwidth levels, and so on, what the implications are of those, I think they have more of a chance getting ready, and being as prepared as they can for exascale. And to be honest, I think Archer 2 in the UK will actually already show people quite a lot where they are. I mean, really, really fat nodes, potentially a lot of messages flying around. Once it's all there, 750,000 cores, that's big. So I think Archer 2 is going to show us really who's potentially ready. But there's, I think the spread is really, really wide.
Good, thank you very much. If there is one thing that you can change in high performance computing, I'm more talking about the hardware. What would that be? If you could change one thing, I mean, is it about memory? Is it about power, energy consumption? I don't know.
Actually, I wouldn't change anything about either the hardware or, I mean, I can't change anything about the science. It is what it is. And I don't have the skills to change anything on the science side. On the hardware side, of course, I mean, you know, if I could wish for the perfect exascale computer, I would have an infinitely powerful CPU with unlimited amount of memory, single threaded, but that's never going to happen. So I don't really want to change anything about the hardware. I think it's quite exciting where we're going. I don't think it's in my gift to want to change it. What I would change, and I think is actually something I can change, is the fact that supercomputing needs to be recognized as a scientific discipline in itself. So you have computer science. Everybody knows what computer science is. You have science by computation or computational science, where people use computational resources to do their science. But what you don't really have is supercomputing science, which is everything that you need to make applications and code scale really well. It's not computer science, because computer science may look at a network, but it doesn't look at the vast scale of the network. Mm-hmm. It may look at node level design, but not at how you tie it all together. So the one thing about HPC supercomputing I want to change is the fact that getting, you know, performance efficiency in supercomputing application is a discipline in itself. That's the only thing I could potentially change. So it's the one I pick.
I could not agree more with you. So I'm very happy you said that. I 100% behind you on that one. Right. I have one final question. So we talked a lot about exascale computing, but also, I mean, we need to think about what will happen next. And I have a question is, where do you see HPC heading in the future? I mean, are we going to keep having incremental changes? So GPUs that are going to be more powerful and more energy efficient? Or do you think we are going to have like a revolution? So a complete change of hardware? What do you think will happen next?
This is a difficult one because so I think supercomputing and HPC is sort of already splitting, and it is going to split even more. And when I say supercomputing and HPC, I actually mean specifically HPC being the sort of very, very, very long tail that will use hardware. I think that'll be largely unchanged, just get bigger. So a lot of applications that can use the cloud now that will use medium to smaller HPC systems. And I think there won't be very much change there for a very long time. Supercomputing at the very sharp end, though, the very big systems, I can see there being much more disruption. But I think the people or communities or codes that actually can use that very, very sharp end will potentially really crystallize into a very few. Whether there will be a massive change in hardware, I don't know. I mean, if I was a fan of quantum computing, I have no opinions on quantum computing either way. But if I was, I would say quantum computing is going to solve everything. I have no opinion on that. I think there will be changes, potentially significant changes, whether they're necessarily GPU or GPU-like, I don't know. But I do think there'll be the polarization between small to medium scale HPC and supercomputing going to the really high end. There's going to be a bit of divergence there. That's my feeling. I may be wrong.
Well, we will see, and we'll chat about that in 10 years, maybe.
Yeah, well, exactly.
Anyway, thank you very much, Michèle, for your time and for your input. I think it was very valuable for the people who are going to listen to this podcast. We would like to wish you, of course, all the best for all your various projects, for Asimov and for Element, part of the ExCALIBUR project. I guess we will interact again on that one, maybe at some point in the future. As far as the podcast is concerned, all the episodes are going to be made available on YouTube and SoundCloud. All the links are on the UK Turbulence Consortium website. Easy to Google UK Turbulence, and we also have a Twitter account, UK Turbulence, the same, and all the links will be posted over there. So thank you, Michèle, again.
Thank you, Sylvain, for inviting me.
No problem. And for everyone else, have a nice day and hope to see you soon in the new episode.